Learning Outcome 3.7. Calculate exponential Fourier series coefficients using properties of Fourier series. You've learned a couple different methods already of calculating your Fourier series coefficients. The analysis integral will allow you to get the Fourier series coefficients for any function. But we're engineers who like to be efficient, and if there's an easier way, we should try to use it. So if we don't need to use that integral, let's find the easier way. Table 3.1 in your book on page 206 shows the properties that exist for Fourier series. I'll demonstrate how a few of these work. You'll work with a few of these in lab number 6, and then we will use something very similar to this in future chapters because these ideas hold with the mathematics of other things we'll be doing. In all these properties in this table, we're assuming that a signal called x to t will have Fourier series coefficients called a sub k. And we're assuming that a signal y of t will have Fourier series coefficients called b sub k. The first property in the table is linearity. This says we can take a signal x of t and scale it, and a signal y of t and scale it, and we can add those two, and the coefficients for x of t will get scaled, the coefficients for y of t will get scaled, and those pairs will then be added. What you see on the inputs, what you see on the output, linearity, additivity, and scalability. Let's look at an example. If we have an x of t that has some coefficients a sub k, we want to scale that x of t by 2, the coefficients will be 2 times those original coefficients. We don't need to rerun the integral. Time shifting. If we have our signal and we want to shift it by a certain amount, we can take those coefficients, multiply by e to the j, k, omega naught, t naught, where t naught is the amount we're shifting it by, and omega naught is based on the period or fundamental frequency of our signal. Time scaling. This is something you cannot do simply using LTI properties. This has to do is because we're talking about Fourier series and the Fourier series integral. If we want to stretch or shrink a function by a certain factor alpha, the Fourier series coefficients won't change. All we have to do is change our values for omega naught. So if we take our example signal, we want to shrink it by a factor of 2. We use the same a sub k, but our omega naught is based on a t that's half the size of the original t. Time reversal. If we want to take our signal and mirror it in time, we take our Fourier series coefficients and we rearrange them such that when we started initially with our k at negative infinity and had a list of coefficients to k as positive infinity, we're now going to read them off in the opposite order. Or we take the equation for them, and everywhere you see a k, replace it with a negative k. So if we had a signal like this, and we wanted to know the Fourier series coefficients for a signal like that, we just need to replace every k in the equation for the coefficients with a negative k. Why do we want to do this? Let's say for some reason you wanted to get the Fourier series coefficients for this signal. This signal can be built out of a triangular pulse, and we can find out the Fourier series coefficients for that triangular pulse. If we were to add to it a rectangular pulse, and that had Fourier series coefficients b sub k, we'd be good to go. But the rectangular pulse starts off centered at time 0. So we need to apply a shift in time to bring it to where we want it to be, and that's going to involve multiplying by a complex exponential. Note that because we're shifting to the left, it's t minus a minus t naught, so our shift is minus t naught. So our final signal would be our triangle plus our shifted rectangular signal, which will have the Fourier series coefficients a sub k plus our b sub k that our coefficients have then been shifted. And that would give us the signal that we were looking to get.